Let us in this video have a look at circuits and the current in a given circuit. So whenever we are talking about a current, it is a good idea to take an analogy of cars moving on a road or traffic moving on a road. So let us take a simple circuit. Let's say I have a battery here. For now we'll just ignore the battery for now, and this is the remaining circuit. And let's say I have a resistor here, so it's a pretty simple circuit, and I have the wires. Now how do we imagine this and understand this, or rather visualize this to understand what's going on? So there's some current which is simply the flow of electrons inside the wire and inside the whole circuit, right? So let's say we have some electrons moving in this direction, right? And let's say we have 5 electrons at this point moving every second. So let's say I am standing here at this point and looking at the wire somehow and counting the number of electrons that are passing. So let's say I wait for a second and let's say 5 electrons pass. So I can say that the current is the charge on 5 electrons divided by a second, which is simply whatever you get, right? You can calculate that. So if 5 electrons pass at this point, obviously those 5 will keep on traveling, and let's say another person standing here, so even he should, so let's say I'm counting every second 5 electrons are passing at this point, and it's a constant current. So if this person counts, even he will count 5 electrons every second, because if 5 electrons pass here every second, those 5 electrons have to reach here because there is no other place to go, right? If let's say only 4 electrons end up here, 1 electron is missing. Where did that go? There is no exit in the whole, in this section between the two people, so that electron cannot go anywhere else. So if 5 electrons enter from here, they have to reach at this point because there is no other way, right? And similarly it continues going on. Now how do you imagine a resistor? Well, a resistor opposes current. So if you're imagining these electrons as cars and the current as traffic moving on a road, so we can imagine this plain section of wire, I mean the section of wire that has a very low resistance as a national highway. So you have a national highway on this section, which is a pretty broad road, and the traffic flows very easily here, and so the cars are moving easily here. But here, let's say this is a bad section of a road. This is a very tiny narrow road here where the cars slow down. But if there's only one road where you have highway or a good road on till here, and then a small rough section here, and then again you have good road till this section, till this point. So now if let's say 5 cars are passing at this point, and if there's a traffic jam at this place because the road is bad, so obviously the cars would have to slow down in the whole road behind it, right? Because that is what happens if there is a traffic jam in, let's say, BCS, then obviously the cars in Khalini will have to slow down because there's a traffic jam ahead, right? That is why you see so long traffic jam lines. It's not that the whole road is bad. Even if a small section of the road is bad, the whole road will be jammed, because that is how cars work, right? If there's no other way for cars to go, they'll have to slow down. So when we say that a resistor opposes current and slows down current, so the whole current in the whole loop has to slow down because of this small section of resistor that opposes current. So it doesn't mean that electrons will move fast here and simply slow down as they reach there. No, without the resistor, if there's only the wire here, then it's like a national highway in the whole loop, and cars will run very fast here. So that's like connecting a wire to a battery, and that is simply short circuit. There's too much current there. But if you have a small resistor here, it's not that the electrons will move very fast here and slow down here, or the current will be too much here and it will reduce here. No, current has to be the same because it has no other place to go. So the whole current in the whole wire will slow down, will reduce, or the electrons will slow down in the whole circuit. And yeah, that is how a resistor reduces the current, by opposing the current. So that is how it works. And now let's say I have a loop, I have another section here. Let's say I have another resistor here. Now what happens is, let's say this guy at this place, he is counting 5 electrons per second. Now at this point, when the 5 electrons reach here, they have 2 options. Either they can go here, or they can continue further ahead in this section, right? They have 2 options. So now the current will obviously be divided. Let's say 3 electrons go on this path and 2 electrons go on this path. Now in what ratio will that current depend? Will more current pass through this, or will more current pass through this? Well, that depends on which has a lower resistance, right? Let's say if this has a lower resistance, which means it is like a less worse road, and this is a higher resistance, which means this is a very bad road. Obviously more cars would like to go on the good road, right, the better road, and that's why more electrons would like to go on that path that has lower resistance. So more electrons will go on that side as compared to this side. So yeah, that is how current behaves at a junction. And our common sense says, so if let's say 5 electrons are moving in that direction and 3 electrons go there, obviously the remaining 2 electrons would have to go there. So what we can see here is that if 5 electrons go into the junction, into this point, the junction, 5 electrons have to come out of the junction. So 3 here plus 2 here, 3 plus 2 is 5, so 5 electrons come out. So what we say is that if 5 electrons go in, 5 have to come out of that junction, and that is pretty common sense, right? The amount of current that goes in, if 5 amperes of current goes in, 5 amperes of current has to come out either this way or that way. So in total, the total amount of current that comes out has to be 5 amperes, because current has nowhere else to go. There is no magic leakage here, and it has to come out either this way or that way. So that is something that we can understand through our common sense. But there's this guy called Kirchhoff, I'm not very sure about the pronunciation, and this person just called it a rule. He made a rule out of this, and this is called the first the junction rule of Kirchhoff, or the first rule given by Kirchhoff. And that simply says that the amount of current that goes into a junction has to be equal to the current that comes out of the junction. That is pretty common sense. I don't think you need to memorize that. But yeah, we'll learn in the next video that this very simple and basic common sense thing is a very useful thing to be used when we solve complex connections like this. And yeah, a brief thing about how do we do that. Well, we can simply form equations by using this very simple fact, which is that let's say there's some current, let's just give that a name, I1 here. So there's some current going in that direction, I1, and there's some current going in this direction, I2, and some current going in this direction, I3. Well, we know that by this law, the junction rule, that the current that goes into the junction, which is I1 here, has to be equal to the current that comes out, which in this case is this plus this current. So it's I2 plus I3, and yeah, I have formed an equation, I1 equals I2 plus I3. For now, that seems a very simple equation which seems to be of no use, but we'll see when you solve questions, you'll see that this, by making such simple equations, you can make an equation for this junction, you can also make one for this junction, which is essentially the same equation again. But yeah, you can make such equations and solve very complex circuits. Just to summarize what all we've covered in this video. So first thing, if I have a circuit, any circuit actually, here's the battery and here's the remaining circuit. So if I have only, let's say, a single resistor here, the current at any point in the whole circuit, in this whole loop actually, has to be the same, because if there's some amount of current going here, let's say we visualize this as cars. So let's say if we have some 5 cars moving from here every second, those 5 cars have to end up at this point also, at this point also, and at this point also, right? They cannot stop anywhere, they cannot move out of the circuit anywhere. So those cars have to end up at this point. If you're talking about a highway, let's say a loop, a highway that is in a loop. And if you talk about electrons, similarly, electrons, if 5 electrons are moving from here every second, those 5 electrons have to end up at this point, and so even at this point, those 5 electrons will be moving every second, and similarly at this point and at this point and at all the points in the circuit. And that is a simple reason why current in a circuit, in such a circuit, is same at all points. Now let's say we just add another circuit, another resistor here of any resistance. Now what we say is that, so these two resistors are in a parallel connection, which means they are not in series but they are parallel. They're not one after the other, they're in parallel connection. So now if we have some current moving in this direction, obviously the current divides and some current moves there and some current moves in this resistor, and the amount of current in the two resistors depends on the resistance of each resistor. And so what we say is that when we have a parallel connection of resistors, the current divides, and it may divide in any ratio depending on the two resistances. So yeah, that is what happens when we have a parallel connection of resistors. And just for completeness, let us take two resistors in simple series connection. Here's the first resistor and this is the second resistor. Okay, yeah, so let's say we have two resistors again, this time in series, and the two resistors can have any resistance. Now if I have 5 electrons moving at this every second at this point, those 5 electrons have to end up at this point and also at this point and also at this point. So at every point in the whole loop, because there's no other path, there's no divergence in any point where the electrons have an option to move either in one way or the other. So let's say though 5 electrons enter at this point into this resistor every second, those electrons also have to move out of this resistor an equal amount at the same rate, and then those 5 electrons have to enter into this resistor every second and they have to exit the resistor. So the current that goes into this resistor has to come out here, and that same current has to go into the second resistor irrespective of what the resistances of the two resistors is, and that current has to come out of the second resistor and back into the battery. So in such an arrangement where the two resistors are in, or not just two, any amount of circuit components, be it resistors or anything else, the amount of current when we have a series connection like this has to be equal at all points, because current has no other place to go, and if some amount of current goes into the circuit from this point, it has to exit from this point into the second resistor and out of the second resistor. So yeah, those are the basic things that we've understood. So yeah, that's it for this video.